If you're looking at this lesson title and thinking, wait, I thought we already talked about intervals of convergence, then you'd be right, we have. But we have only discussed intervals of convergence previously for geometric power series. And in order to determine the interval of convergence for a non-geometric power series, what we have to do is look at the endpoints found from initially finding the radius of convergence. So essentially the process is going to be pretty much the same as what we've done before. We're still going to apply the ratio test to come up with our initial interval of convergence, but we're then just going to have to check the endpoints, find what happens when we plug in those values of x in for our endpoints, and see, does my series converge at the specific endpoints? So let's go ahead and do an example, and I think that'll help you kind of make the most sense of this here. So let's take a look at this particular series. If we say, all right, let's look at this series and do the ratio test. So let's just go ahead and write that. We're going to do the ratio test to start off. And what that means is we're going to take the limit as n approaches infinity and with the absolute value of our terms. So we're going to go x minus 5 to the n plus 1 power. Remember, we're finding the next term, the ratio of the next term divided by our current term. So then this would be n plus 1 times 3 to the n plus 1. And if I go ahead and divide all of this by my current series, remember that anytime you divide by a ratio, it's equivalent to multiplying by the reciprocal. So I'm just going to go ahead and write that denominator here in the numerator. So we then have x minus 5 to the n. Now, coming up is my very favorite thing to do in all of math, which is to simplify fractions. I know, it's nerdy, but I'm a math teacher. So we're going to go ahead and we're going to start dividing here. All right, so let's ask ourselves, is there anything that can divide into another term? Well, if we pay attention and remember our rules or the properties of exponents, we can say that x minus 5 to the n will divide into x minus 5 to the n plus 1, so that all that's left over is x minus 5 by itself to the 1 power. In other words, if our bases are the same when you're dividing, you simply subtract the degrees. Well, what else can we divide? Kind of going the opposite way, 3 to the n can divide down into this denominator so that all that's left over is just 3. Now, what I often like to do with the ratio test is ask myself, okay, what are the terms that are not, or terms or factors that are not being affected by my taking the limit as n approaches infinity? Well, I have x minus 5 here, and I have this 3 down here. So I'm actually going to move that to the outside. And so I'm going to write the absolute value of x minus 5 over 3. And you could totally leave this on the inside. That's fine. It's just clearer for me when I'm working and finding limits to just focus on what's going on with my n values if I'm taking the limit as n approaches infinity. Now, in both of these cases here, I probably should write this inequality here. Oftentimes I'll just find a limit just so I could pay attention to what's going on there. But remember, what we're looking for with the ratio test is what are the values of x? Kind of big picture. What are the values of x here such that this ratio between consecutive terms is going to be less than 1? Well, if that ratio between terms is less than 1, the ratio test says that this series converges. So for what values of x is this true? That's kind of the larger picture of what we're doing here. Well, let's take a look at this limit. Well, what is that limit? That's equal to 1. So I can just write x minus 5, the absolute value of x minus 5 over 3 less than 1. Well, from here, let's just clean this up a little bit. We can write this then as x minus 5 is less than 3, or the absolute value of x minus 5 is less than 3, which is equivalent to writing the following compound inequality. And just so I have a little bit more space to work with, let's make that a little smaller and just say, all right, that means x is going to be between 8 and 2. So just by looking at this, we can immediately establish our radius of convergence, right? We can say, all right, well, it appears that my series is centered at 5, right? So I can kind of almost even draw this on a number line. My series is centered at 5, and it goes all the way up to 8 and to positive 2. So my radius of convergence, R value here, my radius of convergence is 3. Now, what we don't know just yet is what's happening at 2 and at 8. Is my series converging at these endpoints? So that's the second part of this. So now we're going to move on to that part. So let me go ahead and kind of write some space there. So let's check our endpoints. Okay, so when checking our endpoints here, let's let x be equal to 2. So when x is equal to 2, let's plug in, well, let's start setting up the series first. What we're doing here is we're going to plug 2 in for our x value. When I plug 2 in for my x, what do I have? I have -3, so 2 minus 5 is -3 to the n, over n times 3 to the n. And to help me simplify here, I'm going to rewrite this. Because, let me just do that in a different color. -3 to the n can be rewritten as -1 to the n times 3 to the n. Well, if that's the case, and let me just rewrite that down here, what do we have? This is n times 3 to the n. Well, we see that these terms can divide out. So I can just clean that up and say the following. Just remove those and just say that that series, when I plug in 2 for x, is equivalent to -1 to the n over n. Well, does that series look familiar? And it should. What we have here is an alternating harmonic series. So we know that when we plug in 2 for x, we get a series that converges by the fact that it's an alternating harmonic series. I'll just write that. And you could also use the alternating series test here, but we've pretty much established that the alternating harmonic series does converge. Now let's plug in the other endpoint. And I'll come back and clean this up with the entire interval of convergence in just a moment. So when x is equal to 8, so let's plug that into our power series. When x is equal to 8, so again, we're plugging 8 in for this x. So 8 minus 5, that's 3 to the n over n times 3 to the n. And again, we see that these terms are going to divide out. So this is equivalent to the following series. This is equivalent to 1 over n. Let me just write that as well. 1 over n. And what do we know about this series? This series diverges because it's a harmonic series. And again, you can use the p-series test here if you like as well, but just know that this is a harmonic series, which we've established diverges. So let's go back to the tentative, I should say tentative, interval of convergence that we found. We said, all right, we know that x goes from 2 to 8, which has a radius convergence of 3. We've established that it does indeed converge at 2, and it diverges at 8. So we're going to say just less than 8. So this here is our final interval of convergence. Okay? So again, we're not really doing anything that new. Just now we've established a process for checking the endpoints, but we're still using the same convergence tests that we've talked about through this entire unit. I'm going to do one more example with you, one that I think may just establish a couple of other different tests. I would encourage you to pause the video, go ahead and try some of our other practice problems, including finding the intervals of convergence for all of these series here. But I want to jump to something like number 3. I think number 3 is a decent example of kind of covering a number of different concepts here, okay? So first thing we're going to do, again, we are going to do the ratio tests. We're going to say, all right, and I think I'm going to need a little bit of space to work with, so I'm going to see if I can actually move this over here. All right, so let's do the ratio test. Let's find the limit as n approaches infinity of -3 to the n plus 1. Now, one thing that I do want to let you know is since we're taking the absolute value, you can just pretty much remove the alternator or the -1 to the n if it's going to make your life a bit easier when you're trying to find the ratio between terms. I'm going to include it in mine just to stay consistent, but just know that that is an option since you are taking the absolute value of an alternator, which is simply going to make everything always positive. But I'll just write it out for now. -3 to the n plus 1 times x to the n plus 1. Again, I'm writing the n plus 1 term. So this would be then, if I add n plus 1 in for my n, that gives me n plus 2 times root n plus 1. And again, just like I talked about before, I'm just going ahead and dividing, which means I'm multiplying by the reciprocal. Okay? All right, so again, what can we divide? Well, again, just like we did before, this x to the n would divide into this x to the n plus 1, so that just x is left over. This -3 to the n will divide into this -3 to the n plus 1, so that just -3 is left over. And I think here, these are the only values that are not going to be impacted by me taking the limit. So I'm going to just go ahead and write the absolute value of negative 3x times the limit as n approaches infinity of the absolute value of n plus 1 over root n plus 1 over root n plus 2. There we go. All right, and again, we're setting this less than 1. All right, so we know that this limit as n approaches infinity is going to be equal to 1. So we're really just looking at the absolute value of 3x, which is less than 1, which just means if I write this as a compound inequality, we can say x is less than 1/3, but this is greater than negative 1/3. All right, so from here, we can say that our radius of convergence is equal to 1/3, right? We have a power series that's centered at 0, it goes up to 1/3 and up to negative, or down to negative 1/3. Now let's just check to see what's happening at our endpoints. So that's what we're going to check next. So let's let x be equal to our first endpoint, negative 1/3. Well, what happens when we plug that in here? Let me write that in. So we have negative 3 to the n times negative 1/3 to the n all over root n plus 1. Okay? Now, let's take a look at this because I'm going to probably want to clean this up a little bit. Let's ask ourselves, all right, how can I rewrite this? And let me just highlight this here, this numerator, and just think about how I would rewrite this. What do we have? That would be the same as negative 1 to the n times 3 to the n times the negative 1 to the n times 1/3 to the n. Well, if we do negative 1 to the n times negative 1 to the n, that gives me negative 1 to the 2n. Well, think about that. We're saying no matter what our n is, our degree here is always going to be even, which means negative 1 to an even degree power, this is always going to be positive 1. So what this effectively means is that negative 1 to the n times negative 1 to the n just is always going to give us positive 1 for any value of n. Now, what's left over here? Let me do this in a different color. We got 3 to the n times 1/3 to the n. So 3 to the n times 1/3 to the n. And again, if we remember our power properties, that's equivalent to saying the following. Right? Remember our exponent properties, right? If you have a to the x times b to the x, that's equivalent to ab to the x. So I can just rewrite it as the way I've done there. All this to say, well, what is that going to simplify down to? 3 to the n times 1/3 to the n, that's just going to give us 1 to the n. And no matter what n is, this is always going to be equal to 1. So all of this cleans up pretty nicely to the following series. 0, infinity, this is just going to be 1 over root n plus 1. Well, taking a look at this here, we can ask ourselves, all right, what do we know about this particular series? Now, we can't just jump straight to doing the p-series test with this just yet, but what we can do is compare it to a series that we know that either converges or diverges pretty easily. So I'm going to write this, and let me just kind of clear this out so we don't get too distracted here. So we're going to go ahead and compare that to the following series. Let me just move that over. We're going to compare this to the following series. What would make a good helper series here? I would want to compare that to 1 over root n. And what do we know about this series here? This series diverges by the p-series test, because our p-value is equal to 1/2, which is less than 1. Therefore, our helper series diverges. Now, can we apply a direct comparison test here? Well, our series that we started off with here, well, this has a larger denominator, which means it is smaller. So if our larger series diverges, does that mean our smaller series is going to diverge? And the answer is no, right? The only way we would know that this series diverges is if our smaller helper series also diverged. So we can't do a direct comparison test, but we can quickly do the limit comparison test. So if I just say the limit comparison test as n approaches infinity of 1 over root n, so dividing this a sub n by this b sub n, if I divide those, and again, it doesn't matter the order that we divide them, we can just write something like root n over root n plus 1, or we can flip this around. Either way, the limit of this is going to be 1, which is just both positive and finite. So we've established that this series here is going to do the same thing. So this series here is going to do the same thing that our helper series does. Also diverges by the limit comparison test. Okay, so just to kind of walk through the steps here at this endpoint, this is why I wanted to do this problem, because I think it goes through a couple of different concepts. When we plugged in negative 1/3, we found that our series that results from this, our power series, is 1 over root n plus 1. We can't use the p series for that, but we can compare it to a helper series that we know diverges by the p series test. And we applied the limit comparison test and found that this series is also going to do the same thing as our helper series, which means it's going to diverge. Now, in my final color, let me go ahead and do the next part and see what happens when we plug in. Let me just make some space here. Make this a little bit all smaller. Move this to the side. Now let's see what happens when we do the other endpoint, when x is equal to 1/3. X equals 1/3. All right, so when we plug 1/3 in, what do we get here? We get the following series. -3 to the n times 1/3 to the n over root n plus 1. And kind of pause the video right now and ask yourself, what would this simplify down to? And I'm not going to walk through everything again, but hopefully you were able to see that this is equivalent to the following. -1 to the n. Again, if you rewrite your -3 to the n with the alternator factored out, you can kind of see how this would just become an alternating series. Well, what's really nice about this alternating series is it's pretty easy to show its convergence. We can say that A, the absolute value of n plus 2, is going to be less than root n plus 1, right? So our terms are getting smaller in absolute value, right? And then also B, that the limit of A sub n, 1 over root n plus 1, is equal to 0. Therefore, this series here that we have, let me just rewrite it, root n plus 1, converges by the alternating series test. So to put it all together, I know this was a lot, but to put this all together, we have the following. We'd say, from our interval of convergence, which I'll write out here, it diverges at -1/3, but it converges at 1/3, positive 1/3. So here is our interval of convergence, boxed up there. Okay. So hopefully this video was helpful. I'm not going to say smash that like button, but if you appreciated it, hit that like button. Let me know what other questions you may have in Google Classroom.